computing. So I'm going to present you before you can start your talk. Diana Franklin is an associate professor in computer science at the University of Chicago. When she received her PhD at the University of California at Davis in 2002, her research focus was computer architecture, especially new technologies. She has done research in intelligent memories, memory stores, and quantum computers. In 2008, she began her transition to computer science education research. She now leads the Canon, which stands for Computing for Anyone lab, specializing in both 3rd to 8th grade computer science interventions and quantum computing education for devices of any age, with a particular focus toward moving towards more equitable learning experiences. She is currently the co-lead of the Q12 Partnership, a new initiative by the Office of Science and Technology Programs, the National Science Foundation Industry and Professional Organization, to bootstrap K-12 quantum information science education. In addition, she serves on the CRA board and is the author of A Practical Guide to Gender Diversity for CS Faculty from Morgan Claypool. Welcome, Diana. Thank you very much for being here. And please, you can start whenever you want.
Well, thank you so much for having me. I'm very excited to be here. Please go ahead and let me know if I'm speaking too quickly. I'm going to try to speak more slowly than I usually do because I happen to be a fast talker normally. I don't speak any foreign language fluently, and so I am incredibly impressed with all of you who can listen to a talk in a second language. So, so without further ado, I will start my talk. Okay, great. Can you all see the title slide? Okay, wonderful. So today I'm going to talk about quantum computing, and I'm going to introduce it through comics and a game-like atmosphere, because I think that's a more fun way to learn things than just doing math calculations. And so that is what has inspired me in quantum computing to try to figure out how to communicate this through things other than just math. But what is quantum computing and why should you care? So quantum computing is part of the quantum information science, has a lot of aspects to it. It all started out in quantum mechanics, which is mostly in physics with a lot of math thrown in. And that studies sort of these physical effects that we observe in the world. And then that turned into or spawned information theory. And that's looking from a purely math perspective on what can we do with information that follows quantum principles. And quantum information science is all of this together. So it's computer science, it's physics, it's math. It's looking at all of the ways we can use quantum effects in our lives, in products, in whatever we create. So what can we do leveraging those quantum effects that they discovered in quantum mechanics? Right? Quantum computing is one slice of that. Quantum computing is one application of quantum information science, one application of that quantum mechanics. And so that's largely in computer science, but it uses the physics, it assumes that physics, and it uses a bit of math for the advanced calculations. Okay. So I think for learning quantum computing, it's useful to know the history, a little bit of the history of classical computing. So classical computing was designed to automate mathematical calculations that people were doing. And so And in the time since then, we've been trying to make faster hardware and make larger storage. So if we look at where that went, so the first computers were invented, and those could do calculations much faster than we could do by hand. And then in these 60 years of improvement since then, we've had large increases in computer speed, large increases in storage space, and that leads to things that we use now, like Google, which is not only does a search engine, but also Google Maps, routing you when there's a traffic jam, you get routed around it. So all of that requires the computer speed and the storage space, but it was all an evolution from that first computer that was invented. Quantum computing is very different from that. So quantum computing started out with observations in physics about how weird superposition and entanglement are, and then saying, hey, well, these are weird, but how are we going to use these? Maybe we could do some computation with them. And sure, we could do computation with them, but we're competing with classical computing. Classical computing has had 60 years during which there were computers that worked, and engineers have been making them faster and faster and faster and better. So quantum computing does not compete with what a classical computer does well. A quantum computer has to be able to solve problems classical computers do not do well in order to be any better than classical computers. Okay, so it's really what we call a hammer looking for a nail. It's a solution that's trying to find problems that fit it. And so there are many important problems that people believe quantum computers will be able to solve. Okay, so so I'm first going to talk about the problem areas that people believe quantum computing will be able to solve faster than classical computers. And then a little bit about some reasons why you might be interested in pursuing quantum computing in your future. And then I'm actually going to start going through some of the quantum computing principles, starting with the phenomenon in physics and looking at how that applies to computing. So one of the biggest reasons why governments are putting so much money into quantum computers is cryptography. There are lots and lots of messages that have been sent over the internet over the past 50 years, and they were encrypted. And also banks send messages. Okay, this is distracting. Okay, also governments send messages to each other or within, and then we have these spies that take those messages. Well, luckily, those messages can't be decrypted right now by classical computers because encryption is all based on finding a scheme that's easy to encrypt, but takes a very long time to decrypt if you don't have the information to decrypt it. However, there is an algorithm for quantum computing that would make it significantly faster to decrypt things, which would make it feasible to decrypt. And so all of those secret messages that have gone for the last 50 years, we would be able, whoever has a quantum computer would be able to read. That it would need to be a very, very, very large quantum computer, but it is theoretically possible. Okay. All right, so another problem that quantum computers are expected to solve are what we call optimization problems. And so one of them is optimal routing. So for example, we have all of the packages on a truck that need to be delivered. And the question is, in what order should those be delivered to minimize the distance or minimize the amount of time or whatever, as well as if we are an airline and we're trying to figure out what all the routes should be so that the airplanes can come back to the right places, and you have your flight attendants and pilots and they need to get back to the same place. So trying to schedule all of that is incredibly time intensive for classical computers, but it's believed that quantum computers might be able to do that more quickly. And then the final one is molecular simulation. Molecular simulation is very hard to model because it's actually quantum processes. And so quantum processes are very complex. And so they take a lot of space to store the information, and it takes a lot of computation to predict what will happen in the future. If you start with this situation, how will the molecules interact, and what will it be like at the end? And so that's really useful in drug design. Right now, they have a theoretical person who says, hey, maybe we could use this drug. Because I think so for the following reasons. And then they try it in animals and then people or whatever, and they just look at what happens, and they just look at the outcome. They don't know what happens in between. They can only have certain information. And so then if it doesn't work, they're like, well, I guess we were wrong. But if they could actually model accurately what would happen with that drug and the cells that it interacts with, then we would have a lot better idea of whether this drug was designed properly before we actually tried it in real trials. The other one is fertilizer production. Fertilizer production is incredibly energy intensive. It takes a lot of energy. And to make the amount of food that the world needs, we need fertilizer. And so if scientists believe that they could understand the process that is used to make fertilizers, then they could design a more efficient process. All right, so these are very big problems that might be able to be solved, but why might you want to be involved in it? Well, I think one of the reasons is because it's still in its early stages. So that means that there are a lot of opportunities to make large contributions. If you're in a field that's been around for a very long time, then it's harder for one person to make a big impact because a lot of solutions have already been figured out. The other reason is because these are major problems, and if we solve them, that could really change the world. Okay. Another reason is because it is often the case that certain populations get left out of the design team, and we want to make sure that representatives of all societies are in the design team, because we've seen what happens when they're not. So when airbags were first installed in cars, short people got killed. Siri and Alexa didn't, and maybe still don't, I don't know if they've gotten better at understanding people with accents. Facial recognition misidentifies dark-skinned people, and machine learning learns from the past, and the past is awful in many ways. And so it is perpetuating historical awfulness, historical discrimination in its decisions. And these are things that should have been thought of, but the wrong people were on the design, or I will say not enough of different people were on the design team. And so I always encourage people to think about quantum, because you want to make sure that you're represented on the design team, and the best way to do that is to you yourself be on the design team. And then finally, quantum skills relate to other skills. If you pursue quantum, then you could be doing quantum mechanics, which means you're getting a lot of physics. You could be doing quantum computing, which is on top of computer science, which means you understand computer science and a little bit of physics. And it also involves electrical engineering, mathematics, or chemistry. So depending on what area of quantum you were to go into, you would become an expert in one or two or more of these fields. And so even if you didn't decide to continue in quantum, you would have these great skills that could be applied to other jobs. Okay. So there are many ways to choose a career. Maybe some people choose the career because they love that actual work. Like, I chose my career because it had a stable financial standard of living, because I grew up in a household that had very little money, and I wanted to make sure that I could support a family. But it turns out I love coding. It's like I can't believe people pay me to like solve puzzles. That's what I think programming is. And so some people like quantum or programming or whatever, just for the work itself. Some people want to make a big impact, and some people want to make sure they make a positive impact, right? New technologies can also be used to hurt populations. And so some people want to make sure that they're there to make sure that it has a positive impact, not a negative impact. And then some people just want to make sure their options are open. So whatever they choose, they have many choice. They're trained for many things in case they change their mind. So there are a lot of reasons, and you can choose for any or all of the reasons, but lots of people do it for many different reasons. Okay, so now that I've sort of introduced the area, I want to get into sort of more specifically what quantum computing does and how it works. So I'm going to take what I'm going to call the fun approach. So I'm going to try to give you intuition by connecting the physics concept to daily life through cartoons and games or game-like concepts, and then show how those apply to quantum computing. And I know that you've been learning a little bit, so you've had 2 days of quantum computing, but unfortunately, I don't know exactly what you learned. So I apologize if this is something you've already learned a little bit of. If you already learned it, maybe you can enjoy how I'm doing it. And if you haven't already learned it, then hopefully you can learn the concepts themselves. All right, so all computation occurs on ones and zeros that are stored in a bit in a computer or a qubit in quantum. And as a programmer, luckily, we often don't interact with the ones and zeros directly. Those ones and zeros cooperate to become numbers or words or pictures or sounds. So unfortunately, quantum computing is still a little bit in the Stone Age. That's a little person making fire with a stick. And so the beginning of quantum computation is often shown through bit level operations. So instead of quantum computers can do addition and subtraction. They can do it much slower than classical computers. So the idea of this is to, at the simplest level, show what quantum computers can do differently. And today we won't, in only 40 minutes or so, I can't go through actually getting to something useful that they do that's better than classical computers, but at least I can give you a taste of how the physics is influencing the computing and the differences, the things that quantum computers can do that classical computers cannot at that bit level. Okay, so the first thing I'm going to do is start with some quantum gates that act like classical operations. There are classical operations that could do the same thing in a computer today. Okay, so in these diagrams I'm going to show, time goes left to right. So whatever's on the leftmost is what we start with. And then in between are operations, like I could have, like addition or subtraction. And then the result is on the right side. So this would be like, we could have like 4 and 3 going to a plus, and then that would have an output of 7. So in this case, we can see, so we're going to operate with cupcakes because I think that's fun. And so instead of zeros and ones, we're going to be using vanilla and chocolate cupcakes. So the first operation we have is a NOT gate or X gate, and that just flips it. So if I start with a vanilla, I end up with a chocolate. If I start with a chocolate, I end up with a vanilla. Now, I don't want to imply that the qubit is like moving from left to right and going through a machine that changes it. Typically, the qubits often stay in place and lasers are pointed at them, and that's what causes, the gate is actually a laser pointed at them. And they only move to get to another qubit if they're doing a 2-qubit operation and they want to do something together. But they don't, the operations do not move them at all. Okay, so just to see if you understand the not or X operation, go ahead and think for a few seconds about what the output would be if I did 2 NOT gates in a row or 3 NOT gates in a row. Okay, hopefully you all have your predictions. Okay, so in the first case, the NOT goes to chocolate and then it goes back to vanilla. So it turns out that 2 NOT gates in a row are the same as doing nothing. So they are opposites and they just reverse each other. And so if I do it 3 times, then 2 of them counteract each other. And it's like I only did 1. Okay, so then that's from chocolate to vanilla. Okay, so now we'll do the next operation. This is a 2-qubit operation, and this is a swap operation. So in this case, they don't change position, they just swap values. So if I have whatever is on the top initially is going to end up on the bottom, and whatever is on the bottom, that value will be on the top. So they will trade their values. Okay, so and this is not a double NOT, because notice if I start out with 2 vanillas, I do not end up with 2 chocolates. It's if I start out with 2 vanillas, they're already the same, so swapping their values doesn't do anything. They're not trading anything, they're the same value. Okay. All right, so I'll let you think for a second on what will happen here. I see people are putting their guesses into chat. That is fine. So what do people think the first one's going to be? Very good, yes. 2 swaps in a row also counteract each other. They cancel each other out, so it's like they did nothing. Excellent. How about the bottom one? What do we think the bottom one's going to be? Oops. Okay, let's see. All right, yes. So the outcomes are opposite from each other. The first one is chocolate vanilla, and the second one is vanilla chocolate. Great job. Okay, now this is the last classical one, but this one's a little bit trickier because it's asymmetric. So in this case, if the top input is chocolate, that's called the control. So we have 2 inputs, one's called the control and one's called the target. So the control is this.
Diana, I think there's something with your presentation you changed. We're not looking anymore at your presentation. We're looking at some document.
Oh, I see what happened. Okay.
Yes.
How are you
okay.
looking at it?
Okay.
Okay. All right. So now we have a C0 operation. And the spot is the control and the X is the target. So if the one on the spot, so in this case, the top one, if the top one is chocolate, oh, I'm so sorry. This is wrong. Let me just change this slide. Oh, this is wrong. Just a second. I will just change this. Oops. Boy, This is very wrong. Oh, this, you know what? I know what I did. So sorry. Okay. All right. Okay, fixed it on the fly. Okay, so in this case, if the top one is chocolate, the one with the spot, then the bottom one will change. So it's the bottom one will experience a not gate if the top one is chocolate. But if the top one is chocolate, no change will occur. What did I say? The top one is vanilla. I think I spoke wrong. If the top one is vanilla, nothing happens. If the top one is chocolate, the bottom one flips. Okay? Okay. And this ends up being very key to quantum, but unfortunately, we won't quite get there today. But this is a super important operation. Okay, so now go ahead and try to figure out the answers to these guys, and I will look in the chat. This one is definitely more tricky. All right, so let's look at what it would be. All right, so we look at the top one. We first swap them, so then the vanilla ends up on the top and the chocolate is on the bottom. And since the vanilla is the control, that means nothing happens. And so this second gate doesn't do anything, and it ends up just swapping the values. Okay. All right, let's look at the second one. That not gate is going to flip the bottom one, and then the controlled not's going to flip it back because chocolate is the control. And then we have a swap, but the swap won't do anything because they're both chocolate. Okay. Okay, now try this one. Notice I did something a little tricky. I put the spot at the bottom this time. So in this case, the control is the top, but in this case, the control is the bottom. All right, let's look at what happens. So in the first case, nothing happens because the control was vanilla. But in the second case, the control is chocolate. And so we end up with chocolate, chocolate. All right. Okay, so those are three operations that do not use any quantum principles. We could easily do those in classical computers with classical bits. And so now we're going to look at quantum concepts and how they get applied to gates and what that means for our system. Okay, So the first concept is superposition. And so superposition is this idea that you can have two things at once. And so that is an idea that we have in our daily lives, though in a different way than in quantum. So if we look at a computer and say, what would it look like to have superposition in a high level language? Like I'm programming a computer. Well, in a classical computer, I can set a variable's value to say the number 5. In a quantum system, I can actually set that variable to the values 5, 8, and 12, all at the same time. And so I can store more information in a single variable. All right. However, there's a catch. Just because I can store it doesn't mean that I can measure it, which seems like an odd concept, because in classical computing, I put something in a variable and then I read it back out. I use it for computation. I print it to the screen. But that is not how it works in quantum. And this is actually normal in everyday lives. There are lots of things that have complex state that we are not able to accurately measure. Let's take a small child, for instance, who can't talk yet, right? So if I had these two children, I'm looking at this baby and she's either giving me that angelic grin on the left, or she's crying on the right, okay? Now, maybe those are just happy and sad, okay? But even though children can't express their emotions, they do have more emotions than just happy and sad. She could be proud, she could be excited, she could be hungry, tired, angry, bored, anxious. There are all sorts of emotions that a baby could have. Unfortunately, we're not able to accurately figure it out. And so that's a big difference between what the state can hold and what we can detect with our measurement devices. Okay, so what does this look like in computing? Well, let's say I put 3 values into this variable, 5, 8, and 12. If I tried, and these are written in Java, maybe you know Python, maybe you know C, or maybe, don't worry about the exact syntax or the exact way it's written. Hopefully I'll be able to explain it. So let's imagine that the only thing I'm doing is putting the information into the variable and then printing it out again. It turns out that, so if I put multiple values into this variable, when I read it out, only one of those values will be printed out. So sometimes it'll be 5, sometimes it'll be 12, sometimes it'll be 8. And I can't 100% predict which one it's going to be. Okay, it's going to be one of the 3. So that's unfortunate. And that's one of the things that makes it very hard to figure out how to use quantum computing. Okay. This also means that we need to adjust our model a little bit with this new information. So now we have to have a distinction between what the state actually is and what we measure. And when we're looking at something classically, there's no difference. So I have a chocolate cupcake, and then I put it through a swap. I know that now it's a vanilla cupcake because the other was a vanilla cupcake, so they traded values. But until I measure it, I don't know for sure. I can only predict it. So in this case, we're going to put them in boxes, and we're not seeing the actual cupcake. We know that that's the state of them, but we can't see the cupcake itself. And then we have a measurement. And at the time of measurement, we discover whether it's a vanilla or chocolate cupcake. Okay. All right, so this leads up to our new gate. This is a gate that introduces superposition. And so I have a vanilla cupcake. I put it through an H gate, and it turns out that sometimes when I measure it, I get a chocolate cupcake, and sometimes when I measure it, I get a vanilla cupcake. And the same is true with chocolate. If I start out with a chocolate cupcake and I put it through the H gate, sometimes when I measure it, I get chocolate, and sometimes when I measure it, I get vanilla. Okay. So we have this observed outcome, and what it turns out that although I don't know if it's going to be a chocolate or a vanilla cupcake on the way out, what I do know is the probability of whether it's a chocolate or vanilla cupcake. So any single cupcake that I put through an H gate and then measure, I have no idea whether it's going to be chocolate or vanilla. But I do know that if I did this 1,000,000 times, chances are I would have roughly 500,000 chocolate cupcakes and roughly 500,000 vanilla cupcakes. Not exactly, but somewhere around there. All right, so that means we need a way of depicting this state. So what we do is we have a box, and we don't know, notice it's half and half, chocolate vanilla, so it's a 50-50 probability of chocolate versus vanilla. And then we can measure it here. So if we created this with the H from the vanilla, then it'll be in a green box. If we created it from a chocolate, it will be in a purple box. Okay, so why don't we look at the outcomes again? I'm a little bit running, getting a little bit short on time. So, the meaning of the H is that it puts it into a state where it's a 50-50 probability of chocolate or vanilla. It's a little bit more than that too. It's called the Hadamard gate. I will get to the plus and minus. I'm about to be there. Yeah. So why don't I go ahead and just go through this example, and then I'll explain the plus and the minus. Okay. All right. So the first one, oops. Uh-oh. Do you still see my presentation?
Yep.
Okay, great. Okay. So the first one is the purple box, the minus, because it flips it to a chocolate cupcake and then puts it through the H gate. And then on this side, we do the swap. So now we're chocolate on top, vanilla on bottom. And we go through the C naught because it's a chocolate, it changes the second one. And then the first one goes through a NOT gate, and then the second one goes through an H gate. All right, so now let's look at why did I have different boxes? It seems like these boxes should be identical. But here's the crazy thing. If I start with a vanilla cupcake and I put it through an H gate, and then I put it through another H gate, it goes back to vanilla. 100% chance of being vanilla. And if I take the chocolate one and I go through the H gate and then go through another H gate, 100% chance of being chocolate. So these two states cannot be the same. Otherwise, then once we put them through the second H gate, they can't then diverge back to vanilla and chocolate. So there is a very important distinction between them, and it's called phase. So quantum bits don't only store a percent probability of measuring vanilla or chocolate, 0 or 1. They actually have more complexity than that. So they not only have 0 or 1, or the probability of measuring 0 or 1, they have two types of phase, and this is one of them. And so negative phase or positive phase. So when you come from vanilla, you can go to positive phase, which doesn't matter for the measurement of 0 versus 1, but it matters if you go through another Hadamard gate. Likewise, for the chocolate, it's negative phase, and it matters if you go through the Hadamard gate. Okay, so one of the other principles is that because there is a probability of measurement, quantum operations can manipulate, can change that probability. And that's what quantum operations are doing. They're changing the probability, they're changing the phase to try to get the answer that they want. Okay, so that's like using a weighted coin or a weighted die if you're playing games with dice. Okay, all right. So the last thing I'll go through is the fact that Usually when we're used to doing a measurement in the macro world, in the regular world, the measurement itself doesn't change the state, right? If a police officer measures the speed of your car, it doesn't speed up your car or slow down your car, right? When we measure the speed of a swimmer or when someone ends, it doesn't stop them or slow them down or anything. It just gives us information. Okay? However, if you go to the dentist's office and you get x-rays done on your teeth, they put an iron blanket on you to shield you from the x-ray. And that's because x-rays don't only measure, they also destroy. Likewise, if I want to find out how long I can hold my breath, if I do it once, maybe I could do 30 seconds. If I do it again right away, I won't be able to do it for 30 seconds because holding my breath denied my body oxygen. And so now I can't go as long. So my measurement device and process actually changed the state of my body. Okay, that's what it's like in quantum. When we measure, if we have our superposition box, when we measure, it's no longer in superposition. It's not just an outcome. It changed the qubit. And so even though here I got to come back to my vanilla, if I put a measurement in between, now I don't have a 50-50 here with positive phase. I just have a vanilla. So if I were to go through an H gate now, I would now be in superposition. So you can see the outcomes of these two sequences of operations is different because I put in a measurement. So measurement is to be avoided in quantum, which is a big limitation as well. Okay, all right, so just to summarize, quantum computers also store bits just like classical computers do, and bits in both systems work together to be numbers or data. But quantum computers, the qubits, have extra operations and states. They have superposition, they have phase, and this allows more data to be stored at the same time and more operations to be performed at once. Okay? So unfortunately though, quantum state is locked in the quantum bit, and measurement does not tell us exactly what the state was, and measurement collapses the superposition, so we lost that more complex parts of the state by measuring it. Okay, okay. So I will just, okay, so if you at all enjoyed learning it this way, we have games. So all of the graphics I was using is from our game that you make quantum circuits. So you have a starting, you have the cupcakes starting, and then you have what the customers want, and you make a quantum circuit to transform it. And then we have other games as well. So there are actually 5 games. So you're welcome to go and try it. And then that's it. So I can take questions.
Thank you very much, Diana. We are waiting while our attendants are writing their questions. It was such a great talk.
I will copy the
oh yes, that would be great.
URL if anybody wants to go play the games.
Oops.
Oh.
Yeah.
Okay. And also I have a free course on edX. You can audit the course for free, and it goes much farther. So it uses this approach, and then it goes actually to real algorithms with this approach, and it introduces just enough math so that you can also calculate some things. But in this talk, I was not able to get to like, well, what are the really interesting things you can do with that H gate and the C naught, and how can we do stuff with phase? I wasn't able to get to that in just one talk. Okay, so somebody had a question?
Yeah, we have a question from Antonio.
I do.
Okay,
Yes.
go ahead, Antonio.
Thank you very much. First of all, congratulations. The presentation was awesome, very fun. My question is, you said you were in the development side of things. I'd like to know your feedback as to what you think if the current programming languages would be good enough to accommodate quantum programming, meaning can they be retrofitted and then be used for programming, or will there be a need for creating new compilers, new programming languages? Thank you.
Right. So if you want to program at the bit level, there is a programming language called SCAFCC, or that's the compiler. So it uses C and then has additional things put on it so that you can express those quantum operations. So right now, that's fine. But I think that that is still thinking about quantum in the way that I was just doing at the bit level. That is not how we think about classical computing. We think in variables, we think in pictures and characters and things like that. And so I think that someone needs to think about what is practical programming like in computer science and what are the right abstractions for quantum computing that would allow us to design things without going to that bit level.
Right.
But it's not just the language, it's actually the way of thinking. When I design a classical program, I think, oh, well, for each of these, like for each number in my array, oh, well, that's a for loop, right? The control structures exactly match how I break down a problem. And so we need new ways of breaking down a problem for quantum.
Thank you very much, Dr. Franklin.
Mm-hmm.
Okay, our next question is from Hugo Sanchez. Do you believe quantum computing has opportunity of developing in the solution of problems related with geology topics or climate models?
So climate models would fall into the molecular simulation area. And so I'm not an applications person, but basically if we get quantum computers to the point where they can do molecular simulations, I think it's very reasonable to think that we would be able to do climate related things as well. Anything that's involving systems of molecules or atoms or whatever, I think we can predict the effects of these processes better because those models require too much space in classical computers, and like climate models, even predicting the weather, they're not entirely accurate.
Okay. Next question about your games. How many qubits can be used in your games?
Yeah, so in our games, we only have 3 qubits. So they're not an actual quantum computing, right? It's just a game. So we have, I don't remember how many levels we have, 20 or 25, but we only do 3 qubits at a time. Just visually on the screen, it doesn't work to put more. And also we're trying to do it really gradually.
Okay. Next one is from Demian Monterrubio. Would it be helpful to make exact measurements without collapsing the state of the system?
So unfortunately, we can't make measurements without collapsing the state. The problem is that quantum effects are, these qubits are a single atom, or, so the measurement device, no measurement device can exist that wouldn't affect what is measured, right? When a police radar measures the car, think of how big the car is compared to the wave coming out of that radar, right? But in quantum physics, we're talking about a measurement device that's using something of the same size as the effect. And so they interact with each other, and there's no way of getting around that. And so unfortunately, we are always going to affect the state.
Okay, next one from Sergio Alfonso. A great, funny, and very clear presentation. Oh, well, that was just a comment. Next
Happy
one on your.
those.
Okay, yeah, it's full of that kind of comments. From Gilberto Ansaldo, on your games, how complex can we write quantum circuits? How complex?
So we we actually do H gates. So I introduced most of the gates that we do in our game. And then we also have Z gates, which flip between positive and negative phase. And then we actually have entanglement, which is something I didn't get to in this presentation. So again, it's not, we don't get to full-fledged algorithms, but you can make some interesting circuits.
Great. Next one from Fernando Arana. What's the name of your EDX course?
Yeah, so I put an introduction to quantum computing for everyone.
Okay. Yeah, you have already. Okay. You were one step ahead from me. Next one, Rafael Valadez. Thanks so much for this presentation. I have one question about one application on quantum computing. You mentioned on molecular modeling. You say that quantum computers help to enlighten the intermediate steps between the tests they do on animals and humans. Do you think we will ever reach a point where we won't need to, all to test drugs on humans and animals, or the science will always need those types of tests on living beings?
Yeah, I think the science will always need those tests on living beings, unfortunately. I think it will make it much, much better. It reminds me of when I was in 3rd or 4th grade and my teacher said, science, eventually there will be no diseases and science will have solved all diseases. And I thought, but new diseases happen, right? I think that the molecular simulation will be able to simulate some parts of the process, but it won't be able to simulate every single part of the process. We'll discover even more minute parts of the process. And so we won't be able to capture everything in the molecular simulation. And drugs are something that can kill people. And so we have to have a test group.
Okay. Next one from Javid Hikmar. Could you please send the link for the full presentation that you mentioned? Well, that's a request.
Well, I don't have more. I only had one more. So I didn't make the other presents I had. I drew from my edX course to make this, and then I changed the pictures to match the games that I have because we made the edX course before we made the game. So I didn't make any more than I was planning on doing. But like I said, you can go to the edX. You do have to register, but you can take it. You can audit it. So, oh, you know what? You can go to my class website and you can get to the slides without even going through edX if you want. And I also have videos that I made. So if you go to my website, let me just. I will navigate to my class and then. Okay, so if you go here, you have to click on the subject and the slides will, and
Okay.
Okay, and then, all right, so we keep our information in classical ways. Would it be possible to save our information in quantum computers? So quantum computers can store more information, but it's hard to get it out unless all you want to do is compute with it. And the other thing is it doesn't stay for very long. So quantum computers are very unreliable. So anything that you want to store for a long period of time, you're going to want to store classically. And quantum computers, you would only want storage for information that you're going to compute with. For short-term future anyway. I don't like to make predictions about what's going to happen in 30 years. I figure out who knows. Yeah, exactly. Maybe the decoherence. Yeah. Changing qubits but conserving the information. I don't know what you mean by that. So anyway, yeah, because of decoherence, it doesn't make sense to do long-term storage with qubits.
Okay. Well, then that will be the end of all questions we have now. If we
Great.
wait a little bit longer, of course, there will come a little bit more. So I give the word to Dr. Boris Escalante to say farewell from this great lecture. Thank you very much, Diana.
Thank you very much, Diana. It was really fun. Indeed, it was fun. And all these guys that you talked about this afternoon were the topics exactly of this morning's lecture. So it just fit perfect to reinforce what we learned this morning. It was
Great.
perfect. Yeah. But indeed, it's more fun to learn in this way than with lots of mathematics. We're delighted to hear you. It's incredible. I copy your link. I think most of us did. We're gonna dig into your website and course. It was really fun. I'm really happy. I want to thank you on behalf of everyone here, and hope we can see you again soon, and we can maybe interact. Here with us is Dr. Jimeno Alvarez, he also visited you on April. So thank you very much, Diana, for this wonderful talk.
Yeah, I'm happy to do it.
Okay.
And good luck, everyone, in learning quantum computing. I know you all can do it.
Okay, thank you.
Thank you
very much, everyone.
Bye.
See you all. Thank you. See you tomorrow morning. Bye-bye.